What is striking about the theory of gravity is how much it borrows from what the mathematicians were up to in the previous century. They had invented the geometry of curved spaces, not because they were interested in gravity, but because they were interested in settling a very lengthy dispute about the nature of parallel lines that began with an ancient book of geometry written 2,000 years earlier in ancient Greece. But apart from Einstein's groundbreaking theory of relativity, the early 20th century saw a proper revolution in physics. Its magnitude so big that all lines of thought that came before it are collectively referred to by physicists as classical physics. The new lines of thought were called quantum mechanics. Quantum mechanics is as radical as it is successful. Many of the major modern technologies, like lasers or solar cells or microelectronics, are fundamentally based on quantum mechanics. But the quantum world is a very thought-provoking place. Quantum objects can tunnel through walls. They can be here and there, up and down, or dead and alive at the same time. Maybe you've heard of Schrödinger's famous cat. The quantum world is also fundamentally random. I say fundamental because if you flip a quantum coin, not even nature itself is supposed to know the answer in advance. So perhaps you want to ask, well, why am I not seeing any of these strange effects in my everyday experience of nature? Where is all this stuff? The answer is that quantum mechanics is our theory of the smallest things in this world. Things like atoms and electrons and photons that you cannot perceive with your bare senses. But you shouldn't be worried. There are beautiful experiments that showcase these quantum effects in action. And to see one particularly elegant example, you need only to take a look at the 2022 Nobel Prize in Physics. And in fact, we will have to talk a bit more about that in just a moment. Of course, like all other theories of physics, quantum mechanics comes with a whole mathematical model that tells us what will happen in a lab when we do things. So it's natural to ask whether this mathematical model of quantum mechanics only forces us to give up some of the comfortable beliefs we have about what nature does, or if it also is going to force us to change the way we want to do mathematics when we describe the natural world. This is a question that we have been investigating in an international collaboration of physicists. But to tell you what exactly we have done and how we got there, we need to step away from quantum mechanics for just a moment and instead dive into the zoo of numbers in mathematics. We can represent them on a line. In mathematics, we have integers, things like 0, 1, 2, but also -1 and -2. We can use the positive ones to count our coins and the negative ones to count the coins we owe. Moreover, there are fractions, things like 2/3 and -3/2. We can use fractions to split a restaurant bill. One might think that all the numbers in mathematics are either fractions or integers, but this is not quite true. There are also famous numbers that have infinitely many irregular decimals that prevent us from writing them as fractions. The most famous one is the number pi. But still, it has a nice and simple interpretation. Pi is the ratio of the circumference and the diameter of a circle. So taken together, the integers, the fractions, and the irrationals are called the real numbers. And this is a very appropriate term, at least from the point of view of us physicists, because we want to use them to describe real things in the real world. But there is a catch. There is actually another number in mathematics that we cannot place anywhere on this line. To find it, we can solve a very simple equation. X squared is equal to -1. So, to find a solution, we can pull a square root on both sides and say that x is equal to the square root of -1. But what number is that? It certainly cannot be a real number because the square of any number is positive and -1 is obviously negative. So we have two choices. Either we admit failure and say, well, this equation just has no solution. Or we simply elevate the square root of -1 and call it a proper number and say the solution is that. But what does that number mean? There is no such interpretation in the real life. There is no such amount of time, no such mass, no volume, no length, no anything. So you might be forgiven for thinking that this is a cheap math hack to solve the equation. In fact, you would even be in quite good company. The inventor of this number called it as subtle as it is useless. And the famous polymath, René Descartes, gave it a derogatory name, the imaginary number. And ever since Descartes' comments, we denote the square root of -1 by I for imaginary. In the 400 years that have passed since these comments were made, we have learned a bit more. Now we know that the imaginary number is actually quite a useful thing. We can use it to solve a lot of useful equations. And you can see this at play in the great theories of physics. In mechanics, electromagnetism, relativity, we often use the imaginary number as a tool for calculating equations that in the end of the day yield real numbers for describing real quantities in the real world. In other words, the imaginary number is a tool of convenience. If we wanted to bother, we can get rid of it and just do everything with the good old real numbers, but we don't want to because it makes things easy. But what about quantum mechanics? Physicists have for a long time had the uneasy feeling that the imaginary number is somehow hardwired into quantum mechanics. You can see these worries at play in a letter written by the famous Nobel laureate Erwin Schrödinger to another Nobel laureate, Henrik Lorentz, in the early days of quantum mechanics. Schrödinger writes, "What is unpleasant here, and indeed directly to be objected to, is the use of imaginary numbers. Quantum mechanics is surely fundamentally a real theory." So let us try to understand what it is that Schrödinger is actually worried about. First of all, it is not a question of whether the imaginary number somehow exists in nature. This has very little meaning. It is also not a question of whether we need the imaginary number to explain the empirical predictions of quantum mechanics. This is a subtle but important point. So recall that in the end of the day, all the signs in nature that we have access to are things that we see in the lab, the empirical predictions, the predictions for what happens when we do things. But the physics theory is much more than its predictions. It has particles and forces and dead and alive cats. These are the protagonists in the best story that we are able to tell about how nature creates those predictions. But if we decided to get really creative, we could invent a new theory with very different mathematics, featuring no imaginary numbers, that maybe gives us the same predictions as quantum mechanics, and we would never be able to tell them apart in the lab. So the question that you really have to think about, and which Schrödinger is alluding to, is this. If we take quantum mechanics, our dominating theory of nature on small scales, seriously, take it for granted, does that mean that we have to elevate the status of the imaginary number from a tool of convenience to somehow being fundamental? This is the question that we have been investigating and found a positive answer to. This means that quantum mechanics is standing out in the crowd of great theories of physics by making the imaginary number fundamental. It truly needs it to function properly. But to tell you how we get there, I need to introduce you to another fascinating phenomena of quantum mechanics. It is at the heart of this year, 2022's Nobel Prize in Physics, awarded just yesterday in Stockholm. It is known as entanglement. Imagine that we have a lab, and in this lab we create two particles, and then we separate them. One we keep in the lab, and the other one we send really far away. Let's say we send it to the moon. Now, we use our free will to choose some property that we want to measure on our lab particle. Say we want to check its color. Is it red or is it blue? We measure, and say we found that it's blue. We would not expect the other particle, now all the way off on the moon, to take any notice of what we have been up to in our Earth lab. At the very least, some time must pass, so a signal can propagate from our lab to the moon, informing that particle that you should also turn blue now. That is all fine. But here's the thing. If these particles, when originally created in our laboratory on Earth, were put in a so-called entangled state, something that is only possible in quantum mechanics, then none of this would be true. One way of doing that in real life is to shoot a photon, a particle of light, into a special crystal that converts it into 2 photons of half the energy. These photons cannot be distinguished, not because we are bad at distinguishing photons, but because nature doesn't allow us. And by not allowing us, it creates entanglement between them. And then we send off one to the moon and keep one in the lab. Now, if we check what is the color of our entangled particle on Earth and find that it's blue, then the magic of the entangled states allows the partner all off on the moon to take notice of this immediately and also turn to the same color. The 2 particles, although separated by enormous distances, behave as if they are somehow connected with each other. They are entangled. What we want to do is to use entanglement to decide the status of the imaginary number in quantum mechanics. Specifically, we are looking for this: a real-life experimental situation in which the predictions of quantum mechanics for what will happen in the lab, empirical predictions, will be different depending on whether we use or do not use the imaginary number. If such a thing is possible, it means you need the imaginary number to reach the full power of quantum mechanics for predicting real-life situations, which means that it's in some sense fundamental for our understanding of the theory. Unfortunately, it was shown about a dozen years ago that there is no conceivable experiment that can ever be done on a pair of entangled particles that could ever reveal a difference between quantum mechanics with or without imaginary numbers. That is, the real numbers can do it all, no mystery. So what do? Well, the obvious answer, let's have 2 pairs of entangled particles instead. And to make sure they are really independent, we can put one on Earth, 1 pair, and the other pair on the moon. Now we take 1 particle from each pair and send it to a space station. These 2 particles have never met before. They are independent of each other still. But by a beautiful trick of quantum mechanics, known as entanglement swapping, we can make the particle on Earth and the particle on the moon become entangled with each other, although they have never been in the same laboratory. This trick was conceived in the early 90s and then implemented at the turn of the millennium. What it allows us to do is to interact our 2 particles in the space station, usually at the cost of destroying them, but at the gain of relaying the link between the Earth and the moon particle, which are now entangled. Now, back to business with 2 particles. We want to check, for example, the color of our Earth particle, red or blue. We measure and we find that it's blue. How often does the moon particle take immediate notice of this? How often are both blue or both red at the same time? This is a correlation, and we can quantify that. Is it 60% of the time the same, 70%, always? We can measure. What we find is that the prediction of quantum mechanics using the imaginary number is a different correlation, a different outcome in the lab, as compared to any conceivable model of quantum mechanics in which you only use the real numbers. That means there is a real-life difference of using or not using the imaginary number, and therefore it must be fundamental. Speaking now at the end of 2022, this discovery is only 1 year old, but there has already been 3 experiments putting it to the test, although on more humble distance scales. But they unanimously find that the imaginary number is really needed if we want to keep quantum mechanics, but still explain what is going on in the lab. One might wonder what this foundational discovery could have as consequences for the today's rapidly emerging technologies using the physics of very tiny particles. You may have heard things such as quantum cryptography and quantum computation. It is honestly too early to say if or how much this could impact such endeavors. But what is clear is that for us who care about the relationship between mathematics and physics, there is now a very natural question to ask. Should we hope to somehow change our understanding of quantum mechanics in hope of salvaging a model where we no longer really need imaginary numbers and can do everything with normal real numbers? Or oppositely, should we begin to embrace the imaginary number as a welcome fundamental feature in our story of how nature does it.